Hi everyone. First, I would like to thank TVSeminars team for inviting me to give you this presentation. My name is vakili. I'm a principal geotechnical engineer with Mining One and founder of Cavrock, a software company, as some of you might know. My presentation today is a general one, not very technical. And the reason is to actually give you some ideas about our motivations for starting Cavrock and what was our goal and mindset when we thought we need a new piece of software tool in our industry. I will be covering 3 topics. Last year, I attended a conference, AusDrop conference in Sydney, Australia. During the keynote address, Dick Stacey raised this question, and it was very interesting when I heard that. And he mentioned it was a question for him that why back in 70s and 80s there was a lot of significant and notable works in the area of rock mechanic, which we are still actually using a lot of them these days, that were generated, and then after that you don't see in these years as much significant research or results coming out of the rock mechanic research as it used to be. And he answered himself, and he said he realized that when it started, those research works, they were heavily funded by the mining companies, mining industry, which those significant fundings, they don't exist anymore. And he mentioned one of the reasons that he thought could be the main driver for that lack of funding was that initially the mining companies and mines around the world, mining operations, they funded these research projects to get a gain, basically to optimize the mine design, to improve the safety, to increase the profit margins. Whereas a lot of the research after that period, because the people who were doing the research got more and more interested on the science aspect and the research aspect, that kind of lost the track of why we were doing this at first place and why we are looking into rock mechanics as a science in mining and what's the end goal. Secondly, I will just run you through the state of practice and state of art and the big gap that it exists, that we need to close that gap. And finally, I will touch, although it might be a bit not quite relevant, but I think it's doing a lot of damage to the rock mechanic community, a mindset that is advocated and promoted heavily by commercially biased individuals. And at the same time, many rock mechanic practitioners, they're developing this mindset about data, the availability of data, and the complexity of analysis that needs to be done. And I'm being sarcastic here, but the way that I see it is these people advocate that without data, it is better to flip a coin to get the answer. This is probably a bit surprising, this first slide, to see in a rock mechanic type presentation, to see that many dollar values here and there. The table that you see here is actually a work that I was involved, still involved with. And one day we sat with our mining engineer and came up with these estimates. And what it actually relates to is the cost of overbreak or dilution of one single stope in a mine. And when I saw these numbers, and also that graph on the left-hand side is from a famous, well-known paper on the subject on dilution, which shows equally how significant the implication and cost of as little as half a meter of overbreak or dilution can be. And in this case, you see $1 million for a single stope. Open pit example is also another one. The one on the right hand side is again the project that I was involved, and the left hand side shows a well-known paper that shows as little as few degree changes in slope angle, how much impact it can have on the economical viability of a mining project. That's berm, that decoupling berm that you see there, it's, as I said, we were involved with the analysis, and again, speaking with our mining people, adding that decoupling berm, which is a geotechnical berm, basically removes $50 million value of that project. When I hear or heard these numbers more and more throughout my career, the last 15 years in the consulting and being in the industry, first question that came to my head, and I think that's actually the main point that was related to that keynote address of Dick Stacey mentioned, is the fact that if it's this significant what we do as rock mechanics practitioner and geotechnical engineer, are we actually confident that what we do is defendable, is reliable, is accurate? Because the consequences, both from a safety perspective and economical aspect, is quite significant. But what do we do? So what is the state of practice? Firstly, I just want to highlight that we are not trying to point finger to anyone here. This is something that is state of practice. It's all of us we use for design. This is the majority of our industry. They're relying on these methods. And the reason being is that because they're practical, they're faster, they're cheaper, and they're easier to learn and implement. But at the same time, a big portion of engineers, they know that the limitations of these methods as well. And this is not what I say. It's some examples you see here of statements made in well-known papers about reliabilities of these methods and the fact that they should not be used in detailed design. Again, another comment that was made last year by one of the developers of the McCracken Stacey, which is heavily used as the industry standard method for designing raised bore shaft, and the fact that it was originally developed out of 2 case histories. And again, all these just raise a question for an independent person that, are we doing enough? Another example, open pits. Equally, we are using limit equilibrium and empirical methods quite frequently. It's pretty much industry standard method. And at the same time, many of us are familiar with the limitations, maybe less the younger and newer generation that are coming into the industry. And again, as I said, it's because they are fast, they are cheaper to implement, they are easier to learn. But at the same time, the limitations, and in this case, for example, this is a thesis from Chiwaya 2010 in South Africa, which did a really good comparison between limit equilibrium finite element, implicit finite element, and FLAC, finite difference method, and showed a honest sort of independent comparison, and some of the conclusions are I found very interesting. That for example, the conservative nature of limit equilibrium analysis in many respects, and as I'll show you, actually in some instances can be exactly opposite as well, and that's because of the simplifications that have had to be done in order to develop these methods equally with the empirical methods. Okay, so these are state of practice, but actually these are not the only tools that are available. There are actually quite more sophisticated, accurate, reliable, and cutting edge tools available. And I'm sure most of you that are listening to this are well aware of them. I prefer not to mention any of the software names, and this is actually what I've been largely doing for the last, I would say, 15, 16 years of my career, using these software packages. They are quite robust. The results that they generate, they are far, far more reliable than other methods available. But at the same time, they are used by a very, very small population of geotech engineers and rock mechanic practitioners. First of all, because they're very time consuming and expensive. as soon as you tell a mine manager that you need to do a 3D analysis, numerical modeling 3D analysis or something like that, the first thing comes to their mind is expensive. And it's going to take 6 months as a minimum, something like that. The second issue is that many times the results that are coming out of this type of analysis, there's no practical link to the mine design. There are pretty pictures, colorful images and things like that, but it's very hard to actually relate them when you look at the reports that there are over and over cross-sections of plots that for a mining engineer or basically even a practitioner, it's hard to interpret and answer and know how can I push things further, because the results is not really telling me much. There's few plots of stress, strain here and there, but what does it mean in practical sense? One other issue is the fact that I often say that many of these software usually need a PhD or a few years of spare time to be able to learn them. And after that, you're actually just ready to now get into industry, get practical experience and start using them. So that's the issue, that they're hard to learn. And I don't think you can call them practical. So they're slow generally to build and run. They are expensive in terms of the number of hours that are needed to operate this software. And finally, the fact that they're not easy to use. Therefore, this is created this very small group of specialist consultants, and probably myself included as well, that it created this massive gap between the state of practice and state of art. And in CAVROC, what we wanted to close was this gap, to basically make the state of art more widely accessible to all the rock mechanic practitioner and make these cutting edge best practice tools available to everyone in the industry and make it basically state of practice. Okay, now let's get back to that subject that I mentioned to you that we want to discuss. This has been heavily advocated, and I see that especially in Canada in recent months, largely by individuals with commercial biases, advocating these wrong ideas, and I would call it fear campaigns, that they call it fatal flaw or other aspects. And I just want to get down to facts and just let you know, the listeners, what's the difference between the type of analysis that we do and those that is done in geology and statistical analysis. And these two actually in our field, mining engineering, sometimes are getting a bit mixed, because both geology and statistic are heavily included in our type of analysis in mining. First of all, in statistical analysis or geological analysis, similarly, you're dealing with data and the predictive models that are closely related to, because there are regressions basically in simple terms. There are predictive models that are trying to describe how a data population is distributed. This is a good example I usually refer, and it's very valid in this context to say that when you are data limited, if you make more complex or complicated models, you actually end up generating more errors by making model more complex. So the less data you have, it's better to have a simpler model, because the risk of creating more errors is less, because you see it in these three examples very clearly. But this is completely and absolutely different to what we do in rock mechanics and geotechnical design. What we do in rock mechanics is engineering analysis. And this is a really interesting triangle, which is called the mathematical modeling hierarchy. It's in a well-known chemical engineering textbook. And you can see that it's in our analysis type, we have the same sort of things, but whenever you're getting into the empirical or regression equations in the same way, you need more and more and more data, which also is interesting because it also highlights the issues with many of our empirical methods that we are using that are very data limited, and still they're being heavily used in our industry. But when you actually get into more fundamental models, which is numerical modeling, they require more understanding of the physics. So you need more reliability on your physics and mechanics and understanding. And the level of data required to develop the model is not as much, because it's more about understanding of the mechanics and physics rather than just blindly looking at data and trying to fit a curve basically into it. So I hope I sort of explained the difference between these two a bit better. So when you're dealing with statistical and geotechnical analysis, obviously the quantity of data closely relates the reliability of prediction, but also your prediction method is reliant on quantity of data, and its complexity should be corresponding or be related to your quantity of data. But in engineering analysis, yes, both quantity of data, that's your input parameter, and prediction method and the complexity of it, both equally impact the reliability of the prediction. But under no circumstances you can say that because I don't have enough data, my model should be as simple as possible. And that's exactly, I give this example. This is a kinetic equation we use for dynamic support design, or the F equal mass times gravitational force. Imagine that in one of these fundamental equations, we say that because we don't have enough input data, it's better to actually just eliminate one of these variables, let's say the mass in this case, or gravitational acceleration, which is exactly the same thing that if we say, if we don't have data, it's better to flip a coin to get the answer when we want to design. And I just get into another aspect of this discussion, is that what is important, and that's more important to be advocated and promoted, is that if it's for engineering design, it's about how fast, how cheap, and how good it is. And obviously that need to be dependent to the level of study that we are doing as well. But if you can have a much more accurate and reliable fundamental model, numerical model, that you can create and run as fast as the simple one and as cheap as, so it's basically with the same price, it's a no-brainer to go to anything other than that. And at the same time, because of the limitation of the data at early stages, definitely you would expect less reliable outcomes, but that's because of the lack of data. Not because on top of that you added errors into the model as well, the predictive model. I'll give you some examples here. You see example here, 2 tunnels, everything the same, UCS, GSI, depths. What's different here? And whether you have data or you don't have data, if you ignore anisotropy in this rock mass condition, right from the beginning you are causing significant errors and waste of potential. Another example here in another foliated ground. And imagine that whether you have data or you don't have data, how could these two predictions be the same? Yes, if you have less data, you might not be able to get the extent, the severity of damage as much, or you might be conservative, but not that you get it entirely wrong. The failure mechanism and the driving force fundamentally wrong. This is another example in an open pit situation. The limit equilibrium in this case, exactly the same data. Limit equilibrium is actually accounting for strength and anisotropy as well, giving a factor of safety of 2.1. The slope actually was a historical slope. It failed using exactly the same material parameters in a more reliable finite difference numerical modeling basically suggests failed. So factor of safety less than 1. Another project which I was heavily involved in, there's another publication coming for slope stability conference in a few weeks. In this case, when you look at the empirical cases, the factor of safety and limit equilibrium, and even implicit finite element, the factor of safety was marginal, either less than 1 or marginally between 1 and 1.2. And this is before the pit being excavated, and with a more sensible analysis, factor of safety was for a large-scale failure was of more than 1.3. And certainly, you will see more publication of the mine operated and finished and with no major issues and successfully completed. And imagine the amount of waste and loss of opportunities if you have relied on those more simple methods right from the beginning of the study. Okay, let's just wrap it up. Okay, we identified many problems, but we need to provide solutions as well. Hopefully in CAVROC, that's our aim, and we hope we can fix some of these things. But for this presentation, I guess to wrap it up, the important thing is that as rock mechanic practitioner and geotechnical engineers, we need to shift our focus from anything else, whether it's the angle of a crack going here or there, or a micro crack in a certain part of a rock, to what we were here for at the first place, which is for safety and to make mines more economical and make them more efficient and optimized. I might be wrong, but I think we are not focusing enough in our research and development to close the gap between the state of art and state of practice. I think we should do a lot more in that area. And also, as practitioners, we should look outside the usual sources. We shouldn't just rely on X, Y, or Z just because X, Y, or Z names or big names said something. And always questioning the limitations of any design method, including our software, equally. All of them, just make sure you understand what are the limitations of the tool that you're using. And that gives you a much better understanding of how to deal with it and how to actually present it to a mining engineer or mine manager, etc. And lastly, I think this is a killing terminology that is heard more and more in our industry. We always use this excuse that, yeah, we use the industry standard method. Just because it is industry standard, it doesn't mean that it is reliable and it's the best method to use. And I usually refer to this quotation: if a million people say a foolish thing, it is still a foolish thing. Thanks everyone for listening to this. I believe that I will be around when you listen to this presentation, and I should be able to answer some of your questions. Please stay safe and healthy, and I hope very soon we all be back to normal and continue our journeys and normal life. Thanks very much, and bye.